So we're now going to prove the differentiation rule for inverse functions. So we're going to prove that ddx of f inverse at a point x is equal to 1 over the derivative of f at f inverse x. So that's the formula. What are my assumptions here? My assumption is that, of course, f invertible and that f derivative exists at, so here I'm using x for the input of f inverse, so let me use y for the input of f. So it exists at this point, and moreover is non-zero. So perhaps let me make a little drawing here. So if I have x here, y here, and let's call this the graph of f inverse. Then of course this becomes the graph of f if I change the roles here of the axis. If I view this as the x-axis, then this is just a graph of x. But let's not confuse ourselves too much. And the point here is that if I now take a point here x, well, an x on the x-axis, I go up here, and then I get here the corresponding y, which I would call f inverse x here. And if I want to take the derivative of this guy, then, well, I'm supposed to get the slope of this line here, the tangent line. And what this formula tells me is that if I flip the x and y axis, so I flip this graph from being the graph of the inverse to the graph of the function itself, then the slope here is flipped from being, let's say, 2 to a half. That's what this is saying. How to prove this? So proof, and let's see if we can just find a chain of equalities connecting this side to that side. So let's begin with ddx f inverse x, and then write out what it means in the usual way. So it's this thing here. Now, let me for a moment here change the names of the involved things here a little bit. So I do a change of variables. So I instead put here x1 tends to x, then I get this thing here. So the change of variable I did was x1 is equal to x plus age. So I replace all of this by x1. If I solve for age now, this means that age needs to be replaced by this thing here, which I'm doing here. And of course, if age tends to 0, what happens with x1? Well, then x1 tends to x plus 0, so x. So this is all fine. And this can also be seen here. So let me do this. Then if I put a value x1 here, and I want to compute the slope of this thing here, then my difference here is x1 minus x. And my height difference here is, well, exactly this thing, okay? So this quotient should be the quotient of the derivative. Now, let me continue this graph a little bit up, so I can even here put, so now I would call this y1 perhaps, which is f inverse of x1. Well, I basically want to use this triangle to both compute the derivative of this guy, but also the derivative of the function f. So how can I do this? Well, let's see. So now, since I have these two relations here, I can here replace this by y1 and this by y. And of course, this thing here is equivalent to f of y1 being x1. This thing here is equivalent to f of y being x. So I can replace these two guys as well. Here I'm getting f of y1, and here I'm getting f of y. And please notice here that this I can write as the limit, and I'm not writing anything here now. I'm going to think a little bit about what I'm going to write here. But this guy I can move, so this now becomes f of y1 minus f of y divided by this. So here I actually have something that ought to give me the derivative of f at the point y. Now, can I replace this by, so I really want to replace this by this expression here. Is that reasonable? Well, let's see. So we see here, as x1 tends to x, well then, if f inverse is continuous, then f inverse of x1 tends to f inverse of x. Is f inverse continuous? Yes. Well, it follows from the fact actually that f is invertible and that the derivative of f is non-zero at that point. But in order not to be too technical, let's just assume that f is invertible, that f is continuous, and that f is defined on interval. So domain is an interval. Then we have a result saying that then F inverse has to be continuous as well. It's a bit of a mouthful, but let's just assume this. So this means that F inverse is continuous. This means that as x1 tends to x, y1 tends to y. So this thing here implies that we get this limit here. And now we can use the rule for limits, saying that if I have a quotient where, well, 1 has a limit, this has a limit, I can move this guy down below, getting this, which is just f derivative at y. And what was y? Well, y is just f inverse of x. So here this is f prime at f inverse at x. And I'm done. Now this proof is, well, it's perhaps not the worst proof in the universe, but let me just remark that if you want to get a feeling for this formula here, then using implicit differentiation is quite nice. But more on that in a later film.